Hello, everyone. Welcome wherever you are on this world, on this planet. Welcome to this episode of the TUMIVolt Charging Station webinar series. Today, we resume our discussion about the battle for e-mobility, fuel cell vehicles versus battery electric vehicles. And as you may have seen during the last webinar and also our announcements, we have split this episode into two parts. Part one focused on the fuel cell electric vehicle technology, and today for part two, we are going to have a closer look on the battery electric vehicle side of things and the comparison of both technologies. My name is Marvin Stolz, and I'll be facilitating today's session. I work as an e-mobility advisor for the global GIZ project TUMIVolt. And this project forms part or is the e-mobility branch of the Transformative Urban Mobility Initiative, TUMI. And here we focus on the improvement of framework conditions for electric mobility in emerging and developing countries. So to begin this webinar, I would like to show you the agenda, which you can see on this slide. So after a quick introduction of the topic and our expert speaker, Professor Dr. Martin Doppelbauer, we will get his exciting input for, let's say, half an hour, and then we will go into a live Q&A session, which my colleague Lena Stiller will moderate. For your information, we will record today's webinar and upload it to our TUMI YouTube channel afterwards. And there you will also have the possibility to find all our previous episodes of this charging station. For today's charging station, we continue with our deep dive into the two key questions many mobility experts try to answer nowadays. And those are, which technology will drive the future of mobility? Will it be run by fuel cell electric vehicles, or will future mobility mainly rely on battery electric vehicles? At TUMI, we know that sustainable mobility is not about technology only, but sometimes it's still highly important to do an informed selection on the right vehicle technology to power you forward. And that's why we decided to start this conversation about the battle for e-mobility. The word battle might seem quite harsh, but I think it's still appropriate to describe the sometimes heated debates around the competition of propulsion technologies, hydrogen vehicles on the one side and battery electric vehicles at the other. And that's why, we would like to get a better understanding of which technology should be used for each individual application, and if we should continue to see it as a battle even. And to get an educated expert opinion on this topic, I'm very happy to welcome Professor Dr. Martin Doppelbauer. Professor Doppelbauer is working at the Karlsruhe Institute of Technology, where he holds the professorship for hybrid electric vehicles. And at the same time, he's leading the Institute for Electrical Engineering, ETI, and just recently published a book also about the fundamentals of electric mobility. And with his much noted strategy paper on electric mobility and a comparison with hydrogen vehicles, he gained a lot of attention last year, at least in Germany. And we're therefore very happy to have you with us today. So very warm welcome from our side.
Yeah,
but before I hand over to you, just one technical information for our participants. As always, please use the chat function to raise your questions during the presentation. And after this, we will forward all questions to Professor Doppelbauer so that he can answer them one by one in our Q&A session part of the webinar. So I think that's it from my side so far. And with that, I would also hand over the controls to you, Professor Doppelbauer, in a second. There it is. One second, excuse me. To share your presentation. Okay, now it should work. And then I would say the stage would be yours, and thank you again.
Yeah, thank you very much for this kind introduction. Actually, to start with a battle, I'm not really happy with this word battle, and I like to see it more as a complementary technology. And at the end of my presentation, I hope you will agree. But let's see. So we will start with an overview of the current situation. If you look around the world, electric cars are gaining more and more traction, gaining more and more attention. You see the stock of electric vehicles today. End of 2019, we had close to 8 million vehicles in the world, about half of which was in China, and then a significant part in the United States, Norway, Japan, France, and you also see the small green bar that is Germany. Today, as we are approaching the end of 2020, I would assume that we are still already way above 10 million electric vehicles, passenger cars in the world. If you ask, where are the hydrogen cars? Well, basically, they are non-existent. There are practically no hydrogen cars being produced in mass production today. You can only buy prototypes, and the total amount of hydrogen passenger vehicles in the world is around 10 to 15,000. So it's in the range of 1 or 2 per mil of the number of battery electric cars. Now, what am I going to do with you today? We will have firstly an overview of the energy paths, and then we go into some small details of batteries and fuel cells. I will tell you a little bit about the integration of the technologies into the cars. Of course, we have to look at emissions, CO2 emissions. We will also look at the charging or fueling of the cars. And then I have some examples for you for taxis, buses, and trucks, and a short summary. If you look at the technologies of cars, for the fueling of cars, it is important to remember that there are 3 key issues that you have to address. The first one is the production of the energy carrier, which is basically electricity first and then hydrogen second. The second issue is the infrastructure. How do you get the energy carrier from the source to the sink, to the car, to the electric drive? That's the second big question. And then, of course, the energy storage and the supply inside the vehicle is the third big key factor. And all 3 have to be addressed and have to be compared to get to know the technologies better and to understand which of the technologies is best for passenger cars. Let's start with the energy flow. We're looking from the primary energy source to the electric motor in the car. And I'm trying to get my laser pointer. Here we go. First, we have the primary energy sources. Of course, you all know them from oil, gas, coal, uranium to wind, solar, and water, regenerative and not generative. And then we convert the energy so that we get electrical energy. That's always the starting point if we want to use electric energy in a car and we want to use it from renewable sources. In case of battery electric vehicles, we then feed the electric energy through the grid, through a charging station, into the battery, into the electric motor system in a car. That's quite simple and quite straightforward. If we now look at hydrogen, there's a lot of deviation and a lot of additional conversions. That is what you can see here. We start with electric energy, same thing, but now we have a first conversion and we produce compressed hydrogen, CH2. C doesn't mean carbon in this case, it's just an abbreviation for compressed hydrogen. Compressed hydrogen, as we can see later on, is not suited for an infrastructure of millions of cars. Today, we only have a few thousand, a few hundred cars in each country, so that's not a problem. But in future, if we go to millions of cars, we need liquid hydrogen for storage and transport. So we need liquefaction, which is another conversion, and then we end up with liquid hydrogen that we can store, ship, and send to the fuel stations. And then we've got the ultra high pressure tanks inside the car with very, very, very high pressure, 700 bars of pressure. And then we have a third conversion in the fuel cell that will finally, at the end, again, give us electric energy, because we're starting with electric energy, and in the electric drive of a car, we're ending up with electric energy. If we look at the efficiency and the losses in these 2 paths, starting with the direct path first, let's assume, or let's set the electric energy to 100%. We have losses in the grid, in the charging station, in the battery, and roundabout, these are just rough figures, of course, we will end up with 80% of the original electric energy that is available for the drivetrain of the car. Now, with the hydrogen path, we have many more conversions. And you see some typical figures here. I will not go through all of them, but in the end, you can assume that roundabout 15% of the energy, electric energy that we're starting out with, is finally available at the drivetrain of the car, which is pretty much a catastrophe. Let's visualize this result. Let's assume we have 5 wind turbines in a wind park. if we use battery electric vehicles, then one of the wind turbine is producing the losses that are, well, lost in the path from the wind turbines to the car, to the electric motor of the car. And the other 4 wind turbines are producing the electricity that can really be used at the wheels of the car or at the motor of the car. Now let's do the same thing with hydrogen. In that case, 4 of the wind turbines are doing nothing but producing the energy that is then wasted on the way to the car. Actually, the last 5th turbine, in part at least, is also producing losses or producing energy that is lost on the way, and just a part of the 5th turbine is actually producing the energy that can be used in the car. Lithium-ion batteries are a relatively new development. The basics were laid in the 1970s to 1980s in Germany, England, and mainly also in the United States. The technology was then sold to Japan because nobody cared in Germany, England, and the US. And the Japanese developed the first lithium cells, prototype cells, in 1985. And the first product that you can see up here is a camcorder by Sony in 1992. The first electric car that was using lithium-ion batteries, the first battery electric modern car, is this Tesla Roadster, and that was released in 2008. So actually, modern day battery electric vehicles are younger than the smartphone. The current day modern smartphone was invented in 2000 or presented in 2007. Very briefly, I will not go through the details of battery technology. That would be another webinar, of course. But what I want you to understand is that lithium-ion batteries are actually not one technology. There are many, many, many technologies. We have the anode. The anode is mostly graphite, but it could also be other material. And today we're using graphite in combination with silicon. We have the cathode. The cathode is very different materials: lithium, aluminium, nickel, mangan, cobalt, iron, phosphate, titan, oxygen. There are many different materials that can be used also in combinations for the cathode. Even the electrolyte can be very different and can be made of different materials. It can be liquid, pasty, or it can be solid electrolyte. And depending on the application, the battery can be very different and can have very different behavior and very different properties. So please don't make the mistake to judge the performance of a lithium-ion battery from the performance of that cheap battery that you have in your cell phone or in your computer and your laptop. The battery performance of the batteries that are made for cars is a very, very, very different story. This is another graph or a picture that shows you some of the technologies that are currently in use. Here we've got the voltage, the potential between the anode and the cathode. Here's the different materials that are used for the anode. Also, lithium titan oxide can be used for the negative electrode. Here you see some of the materials that are being used for the cathode. And depending on which one you select and how you do the process technology, you get very different performances of the batteries. Speaking of performance of batteries, there's been a development going on. Many years ago, well, 10 years ago, the first lithium-ion cars used NCM111. That is a composite of nickel, cobalt, and mangan for the cathode. And all 3 components had approximately equal shares. And then over time, this developed to NCM622, meaning that 60% now of the cathode is nickel, only 20% cobalt. And it gradually evolved into NCM811, meaning that the cobalt part, which is a little bit difficult because, as you know, cobalt is a costly and also a difficult raw material from the environmental standpoint, is only 10%. The latest batteries from Panasonic that are used in Tesla cars only have 2.8% cobalt in the cathode. And as you will see also later, in the long run, cobalt will disappear completely from the batteries. It will no longer be needed. Also on the anode side, things have progressed. We're using not longer graphite, we're using a composite now of graphite and silicon, which increases the capacity and increases the power density, energy density of batteries. In the long term, you all have heard of solid state batteries. Probably 5 to 10 years, we may have solid state batteries with even better performances. These are just a few announcements that have been made in the last couple of months. Actually, Samsung announced a battery with 50% more energy density. However, this is a research that is going on, it's not production. Panasonic has announced they will increase the energy density by only 20%. However, this is production. They're going to go into production with this. And they will also offer cobalt-free batteries in the next 2 to 3 years. The company CATL is already working on batteries without nickel and cobalt. They will go into mass production this year with cobalt-free batteries in the plant, the Tesla plant in China. Now let's go to hydrogen. Hydrogen cars are much, 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 much older than modern day battery electric vehicles. You can see the first fuel cell car here. It was made by General Motors, and this is already from 1966. So 50 plus years are we talking about hydrogen electric, fuel cell electric vehicles. This is a very brief overview that should demonstrate the complexity of hydrogen systems. It is not just the hydrogen stack, the fuel cell that you need, which is complex in itself, but it's not so very large. What you also need is everything around that. You need a cooling system for the summertime. You need a heating system for the wintertime. You need a high pressure air pump to pump the air into the stack. You need various filters and dosing valves. You need a high voltage battery. Did you know that hydrogen cars cannot run without a high voltage battery, typically lithium batteries, because hydrogen cars cannot recuperate. They cannot restore, regenerate energy that is fed back from the braking process. And they can also not start in the cold with the stack. They need energy to start the stack. So there is a high voltage battery in each hydrogen car. Also, the power electronics is much more complex. You need this additional DC-DC converter. In battery electric vehicles, you only have half of the components. You only have this DC-AC converter and not this DC-DC converter. This complexity also shows if you look at pictures of the systems. And here I have a picture of the Daimler GLC fuel cell system, and you can see all of that. This is not the engine. This is just the hydrogen stack with all of its additional components. And here you see the 2 tanks that are incorporated in this system. And here you see the system of the Tesla Model 3, which is a lot simpler. One of the misconceptions of battery cars is that they are very heavy and hydrogen cars are very light. Actually, this is not the case. Look at the 2 systems that I have here on the screen. The left one has a 430 kilometer driving range and the right one is 560 kilometers. The extra weight of the hydrogen system here is 355 kilograms and the extra weight of the battery system here is 480. But considering the driving range, this is 83 kilograms per 100 kilometer. And here on the battery size, it is 86. So practically the same. However, this is measured according to WLTP. And the fuel cell car is measured according to the new European driving cycle. And we all know that the NEDC driving ranges are much more, let's say, loose and unrealistic than the WLTP. So realistically speaking, the battery weight or the energy storage weight of the battery electric car is already better. The cars are already lighter than hydrogen cars. Here's a picture of the tank of a hydrogen system, which is another relatively big problem because these tanks are under extremely high pressure. You can see they are made mostly of carbon fiber. Carbon fiber is a very expensive material and it's also energy intensive. So there's a lot of energy that's going into the production of these tanks. They have to be inspected every 3 years and after each accident, and they have a lifetime of 15 years, which is usually not a problem. With one of these tanks, I like to call them torpedoes, you can typically get 2 to 2.5 kilograms or store 2.5 kilograms of hydrogen, and that will get you around about 150 kilometer actual driving range, 200 and something kilometers NEDC driving range. Here on the right, you see pictures of the Toyota Mirai that I took myself. One of the tanks in this case is under the seats and another one is in the trunk. On the other hand, the integration of batteries into electric vehicles has a lot of advantages, specifically compared to combustion engine cars. There are basically 2 headlines that should be remembered. The first one is the so-called cab-forward design. Cab-forward design means because you have so little technology that needs to be integrated in the front, you can shrink the overhang. You can make it shorter. So you can bring the passenger, the space, the cab, much further further up. And the other one is the skateboard design. As you can see here, the battery is basically in the ground of the car, providing extra weight and getting out of the way of the passengers. Let's make a comparison between the Hyundai Nexo and the Tesla Model 3. The Hyundai Nexo is the most modern hydrogen car. Actually, there are only 2 hydrogen cars available in the world. It's the Hyundai Nexo and the Toyota Mirai, so the choice is not so big. And I have compared it to the Tesla Model 3 because the Tesla Model 3 is practically the same length, just 2 centimeters of difference. Already in the outside, you can see that the Tesla Model 3 has a much shorter overhang in the front, 20 centimeter more cabin space. And 20 centimeters doesn't seem to be much in the cabin, but actually that's the difference between one class of cars and the next higher class of cars. You may have heard of Volkswagen. They advertise their new ID.3 electric car, that it has the same outside dimensions as a Volkswagen Golf, but the inside dimensions are similar to a Volkswagen Passat. And that's just because of this cab forward design. Let's look under the hood. This is the picture that I took myself of the Hyundai Nexo again. You can see the hydrogen system here. It's full of technology. Everything is filled with technology under the hood. By the way, this is all technology that can go wrong, that can have service problems. And here you see the same picture of a Tesla Model 3. There's so little technology that's needed that you actually have a pretty big front trunk. Let's look at the rear trunk. Again, here, the Hyundai Nexo, you can see there's a big torpedo underneath the trunk. The trunk itself is smaller because you need the space for the torpedo. And here, the same picture of the Tesla, where the torpedo was, you now have a big additional compartment. Tesla calls it a well. Now, let's go to CO2 emissions. Very briefly, these are a picture of typical emissions of typical cars. It's not a particular car. You can compare gasoline, diesel, and then the gas combustion engines with CO2 emissions equivalent per 100 kilometers. They're around about 15 to 20 kilograms. And then if you produce the hydrogen from natural gas, which is what you have today mostly, then you would end up with an emission that is very similar to that of liquid petrol cars or compressed natural gas cars, a little bit better than diesel and gasoline. If you produce the hydrogen from the current electricity grid in Germany, which has still a relatively bad CO2 emission factor, then of course the emissions would be horrible, but I think nobody is going to do that. Now, if you use the same German grid electricity and use it for battery electric vehicles, because the efficiency is so much better, the emissions are much lower. This is the typical situation that you have to do today if you use battery electric vehicles that are fed and charged from the grid. And if you use a home photovoltaic system, of course, the battery electric vehicle is much better than anything else. But it's already much better if you use electricity from the grid. In the future, you would use wind energy probably. And again, because of the losses and the waste, fuel cells are having much more losses and emissions than battery electric vehicles. Of course, the emissions during the operating phase is not everything. We have to look at the production, at the backpack. And one thing that needs to be considered here is that battery electric cars have increased and have improved their energy density. This is the energy density in watt hours per kilogram. That has improved a lot during the last years because battery technology has been evolving very much. And that has led to a much reduced emission in the production phase of batteries. And I will not go through the details here. This is a table that shows you for internal combustion engine cars, battery electric vehicles, and fuel cell vehicles, what are the equivalent CO2 emissions in tons for the car body, for the additional components, for the high voltage system, drivetrain production, the battery itself, the hydrogen tank, the fuel cell system, and then total emissions. If you take this all into account, you end up with a graph like this. On this graph, you can see basically where we're starting, how many tons of CO2 emissions we're starting with at 0 kilometers. Of course, the best is the internal combustion engine because it has the least components. But then during the lifetime of the car, during the driven kilometers, you can see how much emissions are added to the initial production CO2 emissions. And then if you have hydrogen cars, which are the blue lines, The starting point is much higher because of the fuel tank and the system. And if you have batteries, the starting point is even higher, but not so much actually. And during the use case, batteries are much, much more efficient. And so the slope of these curves is much lower. And in the end, typical driving range is 160,000 kilometers in Germany. In the end, battery electric vehicles are by far the most environmental friendly vehicles that you can buy. Let's go to charging very briefly. I want to inform you about the situation. Charging in Europe, at least, also in Japan and China, is now at highways going to fast charging. We have fast charging stations available in Europe alongside each highway, I would say, or many highways. It's going up to 350 kilowatts per charging pole, which is quite a lot, even though we don't even have the cars for that. For buses, there are several systems that are being tried out right now. So this is mass production right now. This is is rolled out in the world, and this is just the prototypes. There's this op-charge standard that can go up to 600 kilowatts for buses. This is a picture of a station. I think it's in Bern, Switzerland, which is using this. So it's not for driving. The buses are just standing there and charging while they're standing. This is just to replace the plugs. But the charging standards are developed further. The next step will be high power charging up to 3 megawatts, possibly even higher than that for trucks. It's being in discussion already to go up to 4.5 megawatts charging power for trucks. So they can charge up in 20 minutes as well. Interestingly, also in China and Japan, fast charging standards are continuously being developed. Just now, a few months ago, 3 months ago, the CHAdeMO 3.0, or as it is called, CHAdeMO G standard has been introduced. It will also go up to 500 kilowatts. It's mainly for the Asian market, and that will be deployed in China and Japan, and the first electric vehicles are expected next year. Transportation of hydrogen has its, well, challenges. You can see 2 trucks here. The first one is liquid hydrogen. The second one is compressed gasoline hydrogen. And if you compare the capacity of these trucks to conventional gasoline fuel trucks, a gasoline fuel truck, 40-ton truck, can feed 1,000 cars with 500 kilometers each, roundabout. Such a truck that we have up here with liquid hydrogen can feed only 530 cars. So that means we need twice the amount of trucks and twice the amount of storage. And remember, liquid hydrogen is very, very cold. So this is a very expensive technology. If we use compressed gas, compressed hydrogen, we can only feed 58 cars from the same 40-ton truck. So this is nice for prototypes, but completely impossible for the mass market. Here you see a comparison of the charging stations. On the left side, you see a single charging pole for hydrogen. You have this hydrogen tank. You have a lot of technology in the background that is hidden in this picture. You can guess why. I didn't take it. And then you have a single charging pole. That whole system costs around about 1 million euros. Here you have 2 poles from an electric charging station. There are many more, of course. And such a single installation, including the transformer, including everything, not just the pole, everything, total costs around about 100,000 euros. So there's a factor of 10 in between. Now, you may say, well, the charging station of hydrogen has much higher capacity. You can charge faster. Actually, this is not the case, because the charging station, the hydrogen charging station, needs time to regenerate after each charging process. So you can charge 1 car in 5 minutes, but then the charging station needs time to prepare for the next car. And that's depending a little bit on technology. The typical charging stations that you have today can serve 40 to 50 cars per day, not more than 40 to 50 cars per day. So if you are waiting in line behind 1 car that has been charging, you have to wait another 15 to 20 minutes before it's your turn. All in all, both charging systems can charge roundabout, very roughly, 1,000 kilometers per hour. So the charging speed of this pole is roundabout the same as the charging speed of this hydrogen station. It's actually not different. And as I said, this costs $1 million euros. There's no alternative. You have to buy it and you have to build it. In this case, of course, you can also do slow charging. with AC, and that will only cost 20,000 euros, and you can charge at home, that will only cost 400 euros. The cheapest charging stations, AC wall box 11 kilowatts, is now on the market for 400 euros. I have some examples here of Chinese buses in Shenzhen in China. This is a city in the southern part of China, close to Hong Kong. They have more than 16,000 battery electric buses now in operation since 2017. They have also, in January last year, converted 99% of their taxi fleet, which is 21,000 taxis, to all electric taxis. Battery electric, that is. Also, trucks are being transferred, but this is a very early stage. This is a picture from the DPD in Switzerland. They are using this 18-ton truck now, which is full electric, battery electric. You can see some data here. The same company also offers, but I'm not sure if they've ever built one, at least theoretically, they offer 40-ton trucks, full electric. So that's already available. At the end, let me go through some misconceptions of batteries and hydrogen and give you a very brief answer. Hydrogen cars can have a longer driving range. Actually, that's not the case anymore, I should say. The best modern electric vehicles, battery electric vehicles, are now in the market with 700 kilometers of driving range. They exceed the driving range of all available prototype fuel cell cars, which are a maximum 660 kilometers. So the driving range on battery cars is generally longer. Hydrogen cars can be refueled faster. Well, you've seen the difficulties before. Mostly this is not the case. And you have to understand that most charging processes, depending on your use case, 90%, 95%, are going to happen during non-productive times, overnight, while you're shopping, while you're at work. So the charging time doesn't matter at all. Hydrogen cars are lighter than battery cars. No, they're not. We've seen it already. The added weight of fuel cell systems, including all the auxiliary devices, is now similar to that of batteries, and batteries are getting better. So in the near future, battery cars will be lighter than hydrogen cars. Today, they're about the same. There is not enough lithium, cobalt, rare earth material for millions of batteries. No, that's also not true. The only special raw material that's really needed is lithium. There is no rare earth material in batteries, and cobalt, as we've seen, is used less and less and less. And by the way, did you know fuel cells also use cobalt as a replacement, as a catalyst, as a replacement for platinum, and platinum is even more expensive and even a more critical raw material. The mining of cobalt and lithium is harmful to the environment. Actually, no, that's not true. Even though you hear it very often, cobalt will hardly be needed in new batteries, and it is needed in fuel cells. So that's the same thing. And today's share is already greatly reduced. And lithium exploration with modern technology is not more harmful to the environment than any other industrial raw material. I've not been going into the details on this, but I have tons of material if you want to know the details. So hydrogen cars are more environmentally friendly than battery cars, and they are not, due to the tremendous waste of electric energy and the large industrial installations that we need for the production, storage, transport, and fueling of hydrogen. Actually, battery electric vehicles are more environmentally friendly. I'm sorry. And then the final thing that point that you often hear as well, we cannot produce enough electricity to run all cars on batteries, which is not true. I have an example for Germany. We would need only 20 to 25% more electricity to run all the cars in Germany, which are 47 million, on battery electric. And 20 to 25%, let's say in a time of 20 to 25 years, is a relatively simple thing. Actually, we would need much more electricity to feed all these cars with hydrogen. So in the end, as I said in the beginning, to close the circle, so to say, I don't think it's a battle really. For cars, the thing is very, very, very clear. Hydrogen technology is not good for cars. It is useful for large installations in industrial environments, professional environments. Hydrogen will be used for long-term storage. That's the main application of hydrogen. Hydrogen will be used power-to-X installations, maybe in aviation, maybe in ships, for industrial process heating, everywhere where you have small power-to-energy ratios. The C rate's much lower than 1. Battery technology, on the other hand, is useful for small installations, for mid-sized installations, including mass market applications. where we have a high output power demand and a high power to energy ratio, the C rate that is much higher than 1, and typical applications are consumer electronics, cars, buses, light trucks, and possibly also heavy trucks. That was very briefly what I wanted to show you today. Thank you for your interest. As said before, I have a book that's brand new, only in German language so far. I'm sorry. If you're interested, you can read many, many more details in that book. Now I'm open for questions.
Thank you very much for that presentation. First of all, Professor Doppelbauer, thanks for giving us these very interesting insights into the efficiencies of the technology. I especially enjoyed your visual presentation on the wind turbines, how much energy you need or lose for each technology. And also the summary you gave is quite clear. Yeah. So what I take home as well is that there are a lot of advantages of the battery electric technology over the hydrogen vehicles, but for vehicles, right? But for the storage and the professional environments, you said it's absolutely feasible. To also use the hydrogen technology. But I would say at this point it's a good moment to start a discussion, and for that I would hand over to Lina, who will, I'm sure, has collected already a lot of interesting questions from our participants. And of course, everyone's still welcome to write their questions into the chat, and then we hope to answer as much as possible. And with that, I hand over to you, Lena. Thank you.
Thank you. So I received some questions through messages or the question chat here in the webinar. As Martin said, I think because we had such good time management so far, we are good to accept more questions and they'll be answered in time. The first question I'd like to bring to your attention, Dr. Doppelbauer, is you mentioned that the rates or the performance of fast charging stations is increasing rapidly. Two questions, actually. How does this affect the lifetime of the batteries? And second, do we need to reinforce our electricity grids to provide enough energy supply? I think this is probably related to Germany. So if you can speak on that.
Regarding the lifetime of the batteries, you have to understand that the charging speed, the power, is very much depending on the charging state of the battery. There are you know all this. You all know these charging curves. You can have the high charging power at the beginning with a low state of charge, and then gradually, as the state of charge increases, the power is being reduced. And if this is done in the right way, it does not affect the lifetime of the batteries. It actually doesn't. If you charge with very high powers at very high state of charges, you may degrade the batteries. But you can be sure that this is one of the topics that's being researched very, very, very in very great detail. And so I would say it's not a big or not a problem at all today. The lifetime of the batteries, in former times, 5-10 years ago, everyone was thinking, well, you probably need 2 batteries during the lifetime of your car, and it's not so long longevity and everything. Today, 200,000 to 250,000 kilometers is the usually average lifetime, I would say, for batteries. So it's outlasting a typical car life. The lifetime that is guaranteed by the manufacturers, there's an industry standard right now, which is 160,000 kilometers. And you can be absolutely sure if they guarantee 160,000, then they will be sure that the average battery lasts a lot longer. Otherwise, they have a big problem. So I would say fast charging done right is not a problem for the lifetime.
Okay.
Second question, we have to reinforce our grid. The simple answer is yes, we have to. Of course, we need 20 to 25% more electricity in the long run, and then we have to reinforce our grid. The grid, of course, has several levels, voltage levels. The smallest problem, I would say, is on the highest level, probably. The biggest problem is on the lowest level, on the 400 volts level, particularly in the large cities in the suburbs, where you have a lot of buildings with a lot of people. There we have actually problems with a low voltage grid. But let's not forget that before we have millions of electric cars, it's going to take it's going to take many years. It's going to take 10, 20 years probably. And so, yes, we have to increase the capacity of our network. But the same is for hydrogen. We do not have a hydrogen network today. Nothing. It's basically non-existent. We would have to build it from scratch. That's even more expensive.
Do you by any chance know of a country or somewhere where electricity grids are actually already prepared for what they would need for more e-mobility on the streets? Or is that just a global?
I would assume that Norway is quite ready because they have so many electric cars.
Okay.
But maybe I should give you some assessments from the energy grid operators today. There are, of course, many companies in Germany, and I have to translate it on the fly. You probably know the company EnBW, which is one of the largest German suppliers. They say Elektromobilität oder die Energieversorgung für Elektromobilität ist keine Herausforderung. So it's not a challenge to produce electricity for electromobility. That's an official statement from EnBW. Okay. And E.ON is another large supplier. They have made, one of the presidents of E.ON has made an interesting statement just a few months ago, and they said they have calculated what would it take to run every car in Germany with electric energy, 47 million we have, and they say the result was surprisingly cheap with respect to reinforcing the grids. That was an überraschend preiswert, surprisingly cheap. So yes, we have to reinforce the grids, but it is not a big problem at all.
Okay, it's an interesting judgment or assessment by German energy providers.
Yeah.
Another question I'm seeing here, I'm just going in the way that they came in the chat now. So the question is, if the 600 kilowatt flash charging for e-bus by ABB, which is run in Geneva, if it's safe for battery health?
Yes, it is, because not the total power is relevant. It is always the ratio between the total power and the capacity of the battery. So if you would run the 600 kilowatts into an e-Golf, it will basically explode. That's not safe. Of course, you don't do that. But if you run it into a, don't try it home. If you run it into a big bus, which has a very high capacity, then it's no problem at all. What is really interesting is the so-called C rate. And I'm not sure if the listeners, the viewers are familiar with the C rate. The C rate is basically telling you how long time it takes theoretically to fully charge the battery. So if you have a C rate of 1, then it takes 1 hour. If you have a C rate, theoretically, the details are much more complicated than that. If you have a C rate of 2, it takes half an hour. And basically, with today's battery technology, we can safely charge at a C rate of 2. There's new technology in the development that will go to much higher C rates, also safely, but the modern day actual current batteries are safe, I would say, very roughly speaking, a lot of details, of course, very roughly speaking, to a C rate of 2.
Okay.
Now, if we have a small battery, let's say I have a 50 kilowatt hour battery, a C rate of 1 means I'm charging with 50 kilowatts. C rate of 2 means I'm charging with 100 kilowatts. If I have a large battery in a bus, let's say 300 kilowatt hour battery, a C rate of 1 would be 300 kilowatts, and a C rate of 2 would be 600 kilowatts. So it's the same loading for the battery, because it's bigger.
I hope that answers the question. I think a very good explanation of how these rates go together. Next question I have for you is, how do you see the future development of long-range heavy-duty vehicles? Would FCEVs or catenary trucks be a possible solution for these vehicle types?
This is a question that often comes up. The short answer is, I have no idea, really. There are many technologies being, I should say that the heavy trucks in their development process towards electricity are far behind passenger cars. Passenger cars have been developed for the last 15 years, 12 years on the market. Heavy trucks have just recently started to be developed for electricity. As you know, there are many different technologies. These overhang wires are being tested. Then we have batteries, we have fuel cell trucks. We have synthetic fuels, which is also an option. What will prevail in the long run? I'm not making any predictions. We will see. My personal prediction is the first thing that we will see in the next years are hybrid trucks. So conventional combustion engines combined with electric engines. And then what happens in 10 years, 15 years, which technology will prevail? We'll have to see. Maybe hydrogen. My personal assumption is synthetic fuel, but we'll see. I'm not sure. Definitely not.
How come,
it's
if I
very
may
different from
ask?
cars. I'm sorry?
What are the criteria that make you think that it might be synthetic fuel that wins the race?
because of the energy density. The problem is, of course, the energy density, and these trucks need much more energy. And it's not the heavy trucks only; it's also how do you say that in English? Mobile working machines, for example, tractors. If you plow a field, you have full load all the time, all the day, from morning to night. You can't even use hybrid technology because there's nothing to regenerate there. It's running full power all the time. So very different requirements than passenger cars.
So the challenge would really be the energy density. If that is increased in other technologies, then that would come into play. Okay.
And even hydrogen doesn't have nearly the energy density of conventional fuels. I've seen research on aviation, planes, and the bottom line was you can't run them with hydrogen, or otherwise you will have to fill the whole fuselage with hydrogen tanks. You cannot have any passengers. The energy density is not big enough.
Okay. Yeah, that's always also a question that comes up. What about aviation and ships?
Yeah. Ships is again a different story.
Yeah. Next question starts with feedback for you. Thanks for the very clear presentation. Could you please go a little bit more into detail when it comes to interurban passenger and freight transport, also heavy-duty vehicles, in countries with poor charging infrastructure for battery electric vehicles? Would you see more advantages for fuel cell electric vehicles than for battery electric vehicles in this specific case?
What type of vehicles we're talking about? Can you repeat that? Not passenger cars, but
interurban passenger transport and freight transport. So it's sort of also asking the same in the direction of heavy-duty vehicles.
Yeah, heavy-duty vehicles, and basically the similar answer. It's not ready yet. This is really not ready yet, I would say.
Does the fact that, because the question also hints at countries with poorer charging infrastructure, does that accelerate your judgment or even reinforce it more, or is that not even?
What do you mean with poor charging infrastructure and low electricity capability? You have no charging structure for hydrogen, so you have to build anything, something. In any case, you either build everything new for hydrogen, which is brand new, or you build new for electricity. You can select which one you want. Usually, electricity infrastructure is much cheaper than hydrogen infrastructure, particularly since there is no mass production for hydrogen infrastructure right now. It's all prototypes. There are no companies that are producing these in large quantities, whereas electricity is very well known. You have the experts, you have the production, you have the companies, you have mass market production. So it's a lot easier to build an electricity infrastructure than to build a hydrogen infrastructure.
And probably also run it in terms of the...
And also run it, yes, absolutely.
Okay. As usual, there is a question also related to Elon Musk that always comes up with e-mobility. So Elon Musk asked for increased global mining of nickel. Will there be a shortage of nickel, or will nickel be replaced by other materials as well, in terms of the battery technology?
Honestly, I'm not an expert in that question. I can only say some stupid things about that. I really don't know what the current nickel production capacity is. We'll have to see. I'm sorry, I really don't know. I'm not able to give a good answer to that question.
No problem. I mean, I think it's even
before
better.
I say something stupid, I'd rather say nothing.
Exactly. So I think some questions, you don't have to be an expert on everything, but I think it would be something interesting to look further into, because what you mentioned about, cobalt being largely replaced.
Cobalt is no problem. Lithium is not going to be a problem at all. We've looked in detail at the lithium production and lithium reserves in the world. We can have billions of batteries. That we already have. And then, of course, we start the recycling process. Recycling is very important. We cannot have a continuous operation without recycling. That's very important.
Next question here goes back to your mentioning of EnBW and E.ON. So the question is, on which ground do they claim that e-mobility is not a problem? That they take peak hour charging in account? Do you know?
Everything. Yes, everything, absolutely everything. They have very detailed simulation models, and I know that in particular EnBW has run field tests in the town of Stuttgart. They have equipped a whole street 100% with electric cars. That was a model they did a few years ago, a test they did a few years ago, and looked at the charging capacities. And this peak hour energy demand for charging electric vehicles comes up all the time. And honestly, I think that is a no issue at all, interestingly, because first of all, you don't have to charge your car every day. The cars have such a high capacity, and the typical daily driving range is so low that you typically only charge it twice a week, or maybe only once a week. And then secondly, if you have a problem with peak power, you can easily alleviate that problem by offering the people a lower tariff in the evening or night hours. And almost nobody is coming back from work at 4, 5, 6, 7 o'clock and needs his car filled up 1 hour later. That's nobody, practically, close to zero. So you need your car ready in the next morning at 6 o'clock or 7 o'clock or whenever you start. And so this peak power demand is actually a no issue, no problem at all. I'm totally convinced of that. It's coming up all the time. There are very stupid calculations from another professor that has just taken up 1 million vehicles and multiplied this with 350 kilowatts and said, this is the peak power, we can never handle that. And this is a no issue. This is never going to happen. By the way, let me finish by saying that the same our challenge is what we're dealing with today with the electricity system that we have today, not regarding electric cars at all. If everyone would turn on their electric oven at the same time, full power, the electric grid cannot handle that. It's impossible. But as we all know, this is never going to happen. It's not a problem. Simply put.
So would that mean that? So if you're saying that, you know, charging times would be delayed in terms of not everyone being charged when they connect the car, but is it then possible, you know, to stretch out all of these people returning, you know, after work at 5, 6 p.m. at night, to stretch them out overnight so that you really lose the peak, or do you just shift the peak somewhere else?
Sure.
Yeah.
No problem at all. If you have for example, rental building with dozens of parties and a big common garage, what is very simple, you can have a load sharing charging. So there is one device that's connected to the grid, and it has the information about the maximum power. And then it's just like a Wi-Fi network, basically. Everyone that connects to the Wi-Fi network, to one single Wi-Fi network, gets a certain speed. The more people that connect, the lower the speed for everyone. And the fewer people that are connected, the higher speed for everyone. The same thing can be done with grids. Very simple. And if you want to motivate people to charge overnight, you reduce the charging fees at 12 o'clock midnight. And you will see immediately they will all program their cars to start charging at 12 o'clock midnight. That's very simple. It's not even difficult.
Fair enough. Let me jump to the next question. So the question is, despite the fact that the first H2 car stems from 1966, there will be a large progress in H2 technology as well, since it was not forcefully driven forward. Will there be a game changer, i.e. in molecular hydrogen storage and other materials?
No, definitely not. We've looked at LOHC, if that is what you're looking at, liquid organic hydrogen carriers, and also the metal hybrid carriers. I can only tell you what I can see. I cannot see a significant advantage there. And particularly, one of the biggest problems is the production of hydrogen from electricity. All these storage systems are not changing that problem at all. It stays the same. And then secondly, another problem is the integration that we've seen into the car, of the system into the car. And that problem is going to be even worse because you need additional technology. You need more technology for LOHC, and you need more technology for these metallic storage systems that are now being researched. And by the way, these 50 plus years of research has been subsidized by European Union with billions of euros. So it's not fair to say that they haven't looked into it. They have. There has been continuous research on hydrogen cars for the last 50 years for billions of euros in the United States and Japan and China similarly. So no, I do not see significant steps that would change the situation or become a game changer for cars, for passenger cars.
Okay. Another question here, going back to the C rate. So the question is loading with C rates greater than 1 always safe? Sort of touches upon what we discussed before, I think.
safe in the sense of safety or in the sense of not harming the lifetime of the battery, I assume?
Probably in then safety for physical harm comes with, you know, a battery being
for the
charged so much
lifetime
that
of the
it...
battery. If we go into the details, it is actually the potential of the anode and the cathode, the voltage of the anode of the cathode that you should not exceed beyond a certain level to make sure that there is no building up of these lithium Dendridenbildung, dendrites, I'm not sure if that's the right translation, of these spikes inside the battery. And to make sure that this doesn't happen, what you need to do or you need to have is very detailed models of the battery. And then you can determine how much charging speed at a certain state of charge and a certain temperature is actually safe. And I mean, this is relatively theoretical talking because we have so many electric cars in the market, 10 million already, many of which are many years old already. And the lifetime of batteries in practice is not a problem, period.
Okay. I'm not starting to argue with you.
Yeah, it's look at the world as it is. It's not a problem. It's not degrading fast.
Okay, then we have, actually the question here is if you agree with the statement that I'm about to read to you. Recycling of lithium is too expensive at the moment compared to the price of lithium.
Yes, yeah, at the moment it's too expensive. Yeah, definitely.
Okay.
The technology, however, is there.
It's not finished yet, the statement though, just 1 second. Because the whole statement goes, there might be green lithium from domestic geothermal power plants in the future. KIT is working on it. Challenges lie in the recycling infrastructure until we have a real system of electric mobility. This will be a big challenge for not industrialized countries. Do you agree?
I would agree. However, I think what we really need is we need to enforce the OEMs, the car manufacturers, that they recycle the batteries that they sell in their cars in the first place. Because this is really a topic and a challenge and also a task for the car manufacturers. They know their batteries best. They know what materials in the batteries. They know how to disassemble the batteries, and they should be enforced to recycle them. And some of them are already starting to do that. Obviously, all the battery electric vehicles, no, not all of them, but most of them are brand new, relatively new, are not near their lifetime. And so the amount of batteries that need to be recycled at this time, at the moment, is relatively small. The technology to recycle them has been developed or is currently developed, and we can recycle, as far as I know, more than 90% of the materials that are inside a battery. Absolutely, yes. This is not cost efficient at the moment. That's why we need some enforcement and just require the manufacturers to do it. But it can be done.
It's an interesting thought, linking it back to OEMs who produce or who sell the batteries in the cars in the end.
They sell them, they should recycle them. That's very simple.
Yeah. I have one question here, which I think we discussed already before, but maybe you have another point to add to. So the question is, if you're shifting peak load to overnight by TOD/TOU behavior, is this not again creating another peak just at another time of day causing overloading? So I think you made the example with the Wi-Fi network where you explained that it would just slow down how much each car is getting out of its socket at that.
But that's two different things. That's actually two different things. With a Wi-Fi network, you're just limiting the maximum peak, so you don't have a problem at all. And the other thing is shifting. If you make it in a stupid way, so that you say everyone in Germany is getting a reduced tariff at 12 o'clock, then you're right, that's creating another peak. But I mean, come on, it's not difficult to have one city at 12 o'clock, the next city at 1 o'clock, and the next city at 2 o'clock. So also, load-based tariffs, so intelligent tariffs that are not just hourly based, this very stupid, simple scheme that I presented before, but tariffs that are dynamic, that say, okay, now we look at the load of the network, it's very low, so the tariff goes down, which is how it's called smart grid. So you have a feedback from your network supplier into your car or into your home, and they tell you exactly at a certain point of time what is the charging cost right now. That will become a commodity because it's very simple to realize. It's very simple to do. You need an internet connection. Everyone has one today. And then you need a very simple controller inside your counter and to do that. I mean, you have to understand, we are not talking about tomorrow or next year. We're talking about the next 20 to 25 years. And the technology to do this is simple and cheap and already available. And that's why I say, and it's not just me who says that. I've given you the references before from ENBV and E.ON, and they have looked into all of these details in much more details than I have done. And they are coming up with a statement. It's not a challenge. We can do this. We can handle this. I'm pretty convinced that this is going to be possible. I'm an electrical engineer at the end of the day, of course.
Well, then I'll give you one last input in terms of on the issue of recycling, which is not so positively outlooking. So a comment is that there are lots of batteries from Prius cars in Mongolia, which are just discarded into the environment. And it's not very simple there to just look at the amount. Oh, sorry. So apparently it's not very simple to make sure that recycling is done properly because there's a huge amount of scrap cars ending up in African countries, as we all know. So.
Yeah. That's a challenge.
Which is, I think, yeah, I think that is probably one of the biggest challenges we're facing with e-mobility. What happens once a car is no longer used and the remaining parts of the car can still be used in different applications. So I think this is my cue. Thank you very much for answering all these questions. I'm happy to hand back over to Marvin because I think we're running out of time.
Yes, exactly. Thank you very much to both of you for this very agile Q&A session. And again, Professor Doppelbauer, I really like to thank you again for giving us your time and presenting your expert views on the current status of battery electric vehicles and in the mobility sector. And of course, to all participants, thank you very much as well for the active participation and your questioning. I really enjoyed it, and I hope you did too. And if you want to learn more about the charging station, of course, you find us on all social media channels, YouTube, Twitter, Facebook, and so on. And yeah, we hope you enjoyed this second part of the battle for e-mobility, which at the end is not so much a battle as we heard before. But of course, we invite you at this stage now to future webinars, which will be coming very soon. And on that note, I'm saying thank you very much again and see you next time. Bye-bye, everyone.
Goodbye.